started, as I said, today we talking mostly about first order logic. It's also called FOXY, first order predicate calculus. Calculus is basically putting together statements and doing inferences. Okay, that's what you do. The normal calculus is the one that does inference on statements made on real value variables. Okay, and first order predicate calculus makes inferences. It allows you to write down your statements in a particular form. You know, we talk about a generalization of propositional logic called first order logic today. One of the most important things is to get used to these guys. That's for all, and this is there exists. Those are what are called the quantifiers. How many of you have seen those? Okay, so most of you know it, so we sort of try to get your intuitions about those statements, those particular connectives. Actually, it turns out you'll see, I mean, just sort of giving a punchline. For all is a shortcut for many conjunctions. Okay, so if you want to say A raw and B, A raw and A Tom and A Mary, etc. So some relation A holds for all of these, you can just say for all X, A of X. That's it. Okay, so for all is a shortcut for conjunctions. And remember that it can be a shortcut for an infinitely large conjunction. Okay, based on what we discussed last class, if I just wanted to, if I say something like for all X loves X, father of X, that's an infinitely large sentence. Even if you have just one object, let's say Tom, and you have father of, then you say loves Tom, father of Tom, love father of Tom, father of father of Tom, love father of father of father of Tom, father of Tom. Okay, so it's a huge conjunction. So that tells you how much of a compression you can get just by throwing a quantifier. Equivalently, disjunction essentially is, instead of, so there exists is a shortcut for disjunction. So if I want to say that at least some people love their father, then I just say there exists X, loves X, father of X. Okay, so there exists is just a shortcut for a big disjunction, and for all is a shortcut for a big conjunction. Just keep that in the back of your mind. A lot of things will fall into place in terms of the syntax of logic as well as in semantics. But to some extent, actually, these two guys, you can see almost how they can allow you to say infinitely large number of statements in a shortcut, right? Because, as I said, remember this, for all X loves X, father of X, that's actually an infinitely large statement. You really have to understand that. Okay, the moment you have one functional term, it becomes an infinitely large conjunction. And you could just write it in like a little single sentence. So an amazing amount of compression in writing a program. Okay, so that's sort of like a quick start of the class. Again, so this, by the way, is a limerick written by a guy called Henry Coutts. Henry Coutts actually has this list of limericks called AI limericks, and you can look it up back in like 80s, and this is one of them. And in general, of course, first order logic, you can see today, and I mentioned it kind of earlier on too, that first order logic has a huge history in the human race. It started in like before Christ, when Greeks were thinking about how to do propositional logic. We'll show like a slide, sort of makes you feel as if this is a real historic class, because it's like started sometime then, and they finally figured out how to do sound and complete resolution for first order logic in only 1962. Okay, and so pretty impressive long arc of human evolution captured by first order logic. And so, in fact, knowing a lot of terminology for first order logic, even if in fact it's not currently the hottest way to do certain kinds of, basically the resistance and so on, it will actually, it's a very important piece of human knowledge. And in fact, you will actually, a lot of things will fall into place if you understand the jargon of first order logic. And of course, the rest of computer science uses first order logic. Yes, sir.
I was going to ask, what was the breakthrough, or why did it take so long to for the soundness and completeness?
We will see that. Oh. Okay. Any questions before I get started? Okay. So I showed this last time. I said after propositional logic, I could run a whole bunch of things, and then I decided to focus on first order logic. Just remind you. And then, of course, first order logic falls in our big table of logics. Propositional logic thinks the world is made up of statements that are either true or false, and first order logic thinks the world is made up of objects and relations between them, and the relations may hold or not hold. So the statements that you are talking about in propositional logic have further structure. Okay, atomic model is just a state. State is a black box. By the time of propositional models, you say a state is made up of propositional statements that are either true or false. Okay, and by first order logic, you are the relational logic, you are saying these so-called true-false statements, they're really statements about relations between objects. And so, in fact, you are further splitting this into having more structure. The world is made up of objects and the relations between them. So, in particular, in first order logic, you have a name for a thing for actually talking about relations, and that's what is the predicates. The predicate part of the first order logic, first order predicate calculus, is a predicate is a symbol that sort of represents some real world relation. And then there is a term, a technical term called term, T-E-R-M, term. And the term is a generalized object referent. Okay, we'll see this again in the next slide. Okay, so you basically first order logic sentences are made by talking about what sorts of terms do you have. How do I make, given a term, how do I make generalized terms? A generalized term is an address to a particular object in the world. Okay. And then, if I have two referents for, let's say, references or the pointers for objects in the world, then I can say, here, this predicate holds between this object, and this object. That means this relation holds between these three guys. That's what logic, first order logic tries to do. In propositional, in predicate logic, that's what you're trying to do. So that also should make you realize that when I make a statement, predicate holds between object 1 and object 2. That's a statement that is either true or false. Does this relation hold or not? So if you are compiling first order logic to propositional logic, remember we said that is a possibility. It turns out that when you do that, essentially these what are called the atomic sentences. An atomic sentence is a predicate of terms. Again, I'll show you the definition in a minute. Okay, predicate of terms. A predicate of terms corresponds to a proposition symbol, and it can be either true or false. The more atomic predicates, atomic sentences you have, the more propositional symbols you have. And this also explains to you why once you have a functional symbol, all hell breaks loose, because the moment you have a functional symbol, there are infinite number of references to objects. Okay, and so then basically you can write infinite number of atomic sentences, which means there are infinite number of propositional symbols, which means it's infinitely large propositional logical knowledge base. That sort of corresponds to why people were stuck as to how the heck are we supposed to prove soundness and completeness of first order logic. And in fact, eventually when we did figure it out, we figured it out by saying that there is a way of propositionalizing it incrementally, such that essentially if you ever are able to prove a statement in any particular iteration of the propositionalization, the statement is true. If not, all bets are off. And that's why it becomes semi-decidable. When the theorem is true, you will be able to prove it. When it's not true, you don't know whether it just would have taken some more time and you would have been able to prove it, or it's just not provable, which is semi-decidable. As I'm saying this, some of you should be wondering about this other thing, the Gödel's theorem. How many of you have heard of Gödel's theorem? Okay? And the question is, how does Gödel have anything to do with any of this? Gödel, for example, talks about incompleteness. Okay? That in fact what he's saying is that in a sufficiently powerful logic, which is a little more powerful than first order logic. We'll talk about how you can extend the first order logic by a little bit so that you will have mathematical induction thrown in. In that logic, essentially there are statements that are true but still can't be proven. So that means even semi-decidability is gone. That's what happens when you get to more powerful logics. Okay, as bad as semi-decidability looks, it looks like a wishy-washy thing. That before the universe ends, you will be able to terminate if the theorem is true. If not, all bets are off. That looks like a pretty wishy-washy complexity result to be feeling good about. But it becomes worse if you throw in a little more expressiveness about mathematical induction. And in fact, one of the things I will show you a little later is to show that being able to write mathematical induction in the current first order logic that we will look at, the mathematical induction axiom cannot be written in any compact fashion. It needs to be written once for each predicate. And if you can write it as a single compact fashion, then in some sense, essentially it will require quantification over predicates. We'll talk about that again. And that is something first order logic won't allow. The part that makes first order logic, if you're thinking why is it first order logic, is you say for all x there exists x. These x's range over objects. These x's range over objects. Quantification is over objects, or terms, not over predicates. You see what I'm saying? And so because of which, actually, as impressive as this logic is, there are logics that can write stuff even more compactly. And they will be even harder in terms of complexity of inference. Okay? Okay, let's go through. So, and then I also talked about this whole thing last time in terms of atomic to first, relational, atomic to relational to first order, and how you can compile one into other. As long as there are no functional symbols, first order logic can be compiled into predicate logic, which, propositional logic, essentially. So that's something you want to keep in mind. Okay, so finally, the boring stuff, syntax of first order logic. Okay? The syntax of first order logic contains constraints, okay, predicates. These are essentially, think in terms of constants correspond to objects in the world. As I'm writing this, I'm talking about what is it correspond to in the world. In general, talking about what a statement's innards correspond to in the world, that's actually the semantics of the statement. So we'll talk about semantics in a minute again, but right now kind of realize that constants corresponds to objects in the world, predicates corresponds to relations in the world. Okay? Functions correspond to object generators. So a function takes a term as an input and a set of terms as an input and gives out as a term. Okay, so functions are ways of essentially generating more references, more addresses to objects. Okay? Then there are variables. Variables essentially range over objects. In syntax here, variables range over terms. Then there are of course connectives. the usual logical connectives, the and, the or, the negation, the implication, and the bidirectional implication. You know these. These are stuff from propositional logic. Then there is equality. We won't actually talk much about equality directly. I mean, in fact, you can talk about first order logic without equality directly. And then, of course, the very important thing, quantifiers. This is very important because the quantifiers make it possible for first order logic to say in few sentences what propositional logic will take a large number of sentences. Without quantifiers, you can't do that. And the quantifiers, of course, are for all and they exist, and I explained to you approximately what they are. Okay? Yes?
Are those true and constants?
No, true and false are the, well, of course, there are specific constants called true and false. Okay? But that's different from the truth and falsity value of a statement in the word. So true is this symbol which will be holding in every word. False is a symbol which will hold in no word. Okay, you can think of true and false as in the next sentence, next slide we'll talk about atomic sentences. True and false are actually atomic sentences too. They're specialized atomic sentences. But that's different from the truth and falsity value of a generalized statement. Okay? So, we start by building up syntax by talking about first atomic sentences. Okay? An atomic sentence, as I said, is a predicate of terms. That's it. An atomic sentence is a predicate of terms. And a term is either a function of terms, or a constant, or a variable. Right? So if I, for example, have Tom, Rav, X, and like father of, friend of, or father of, okay, FOF, okay, as a function, then Tom is a term, Rav is a term, X is a term, father of Tom is a term, father of Rav is a term, father of father of father of father of father of father of Tom is a term. Okay? So there are essentially, the moment you throw in a function, there are infinite number of terms. In general, in first order logic, one thing that we assume is there are a finite number of constants, and a finite number of predicates, and a finite number of functions, and a finite number of variables, and so on. Everything is finite to begin with. But the moment you throw in a function, you are effectively having an infinite number of terms. Okay? Okay, so if I have this, do people get this notion of what an atomic sentence is? So here are some examples. Brother, King John, Richard the Lionheart. So King John presumably is a constant, Richard the Lionheart is a constant, and brother is a relation. Now, you might be wondering what makes something a constant and something a predicate name, something a function name, right? What makes something a function name in C language or Python? What makes something a variable name in Python or C language? It's just convention. You decide these names I'm going to use them only as variables. These names I'm going to use only as functions. These names I'm going to use as constants. So you can think of it as sort of a type declaration. You can make any function names, any predicate names, any constant names. The only thing you are not allowed to do is to mix something which you have used as a function in one sentence, you use it as a constant in some other sentence, and a predicate in another sentence. You can't do that. That's what you do in writing programs, right? You can make any variable name, any function name. There is nothing in the name itself. It's the consistent use that gives the semantics. I say this because people get confused when they first come to first order logic. How do I know that brother is a predicate? It's a predicate because it's in the place where predicate is supposed to be. So if I write one more sentence where brother winds up being in a place where constant is supposed to be, then you cry foul. Then you say you can't have it both ways, Rob. It's syntactically uncompilable. Okay? Then of course here is another one. This is a more funnier looking, a longer sentence. Length of the left leg of Richard. Richard is a constant. Left leg of is a function. It takes Richard and gives address to his left leg. And then length of is a function. It takes a thingy and gives its length as the output. That too is an object. Length is a number. So I wrote length of the left leg of Richard and length of the left leg of King John. Somehow we are into comparing left leg lengths of English names. Okay? And I make this very interesting statement that it is greater than. That is, Richard's left leg is longer than King John's left leg. That's what I wanted to say. So I said it. And one more thing, by the way, and just to make sure that we are on the same page, I wrote all these nice English names like length, left leg of, Richard, etc. Right? That's just to make you feel good that there is some meaning in these variables. Just because you call something length of, it doesn't become length of in any semantic sense. Just because you call in your program neural network understand is the first function name and then hope for the best. It's not going to do anything. You make it actually do the neural network. Do you understand what I'm saying? We use the names, really in fact, people, this is also important, people tend to confuse naming as if it is the semantics in itself. Just because you wrote the name doesn't necessarily mean that name means the same as what you have provided as the semantics as an English word. In fact, then people actually say, some people actually say, there was a great old paper called AI meets NS. Artificial intelligence meets natural stupidity. Okay, and this was like old times, and a very smart guy called Drew McDermott wrote this paper, and he basically, one of the things that I was saying is at that time people were doing this wishy-washy thinking. They will write like a function name called understand. And it must be understanding because I called it understand. And so what he said essentially is try to write it as G0001. The function name is Jensen. Jensen, by the way, is like make up a new constant, a new name. Okay? So G0001 X. And if it shows behavior that looks like understanding, then you will be happy. Just by calling it understand, you don't expect it to be understanding anything. Okay? That is something to keep in mind, that in fact, as far as your program, that in any logical inference engine is concerned, it doesn't suddenly say, oh, left leg up, I know what left leg up means. It doesn't say that. It basically, as far as it's concerned, left leg up is blah, blah, blah. And that blah, blah, blah has semantics based on how it gets used in all the other terms. There is this word called distributional semantics that has become popular these days in natural language processing community. And similarly, in fact, by the way, this is not just true for logic, it is true for language itself. The meaning of the word can be found by the company it keeps. This is why Shakespeare said, rose by any other name would be just as fragrant. Name has nothing to do with the semantics. Do you see what I'm saying? And in fact, a high mark of intelligence is when you were a kid, you realized this. And you played pretend play. You will say to your parents, let me call this rose dog. And then I'll make sentences about dog. And it doesn't become dog, it will still be a rose. You see what I'm saying? So keep that in the back of the mind. We will just basically follow the same convention that we will use variables that at least capture the intended meaning that the writer had. Whether the program will actually get that intended meaning is all bets are off. That depends on what you have written, along in what other sentences you have written. Okay. So that's and then you cannot have predicates of predicates. You can only have predicates of terms. And a term is either a constant or a variable or function of terms. The fact that you can't have predicate of predicates or you cannot quantify over predicates is what makes this first order logic. When you say second order logic, you can also quantify over predicates. Okay? Now, connection to propositional logic. Think of atomic sentences as propositions. That's it. In any language, in fact, actually what you should say is ground atomic sentences. This is very important. Ground atomic sentence is a sentence where the terms don't contain any variables. You see what I'm saying? Because if I put a variable, I don't quite know what it is actually ranging over in that atomic sentence. Okay, a ground atomic sentence is both of these are ground atomic sentences. Brother King John, Richard the Lionheart, that's an atomic sentence because it's a predicate of ground terms. No variables. Ground means no variables. A greater than length, left leg of Richard, length, left leg of King John, that's also a ground sentence, ground atomic sentence. The nice thing is you can think of them, even though you put some nice parentheses and commas so that you feel good about predicates and terms. If need be, you can say this is really a big preposition name. So brother dash King John dash Richard the Lionheart. That's one single name. That is your preposition term. That can be either true or false. And similarly, greater than dash, length left leg of Richard dash, length left leg of King John. That's a huge big single variable name, a single name. And that is another proposition. So this is how you convert predicate sentences into propositional sentences. So really an ground atomic sentence is just syntactic sugaring with a little bit of parentheses and nice beautification with commas. Okay? To talk about actually what underlying it all is a proposition symbol. This is exactly what happens in when you convert like a Python, a C language to an assembly language. Right? So the structure goes away and it will become an assembly language program. Assembly language is hard to look at, it hurts your eyes. But there are inference engines for assembly language. The Intels and the Motorola's. Motorola is kind of dead, Amda's. Okay? Any questions on this? Yes?
So to define functions, do we write function bodies in predicate logic?
No. That's a very good point, actually. So the function is just used by just using that function, okay? And then you write more and more and more sentences involving these functions and the predicates and the constants, and the meaning sort of flows through. Now again, one of the interesting things is some of this stuff was hard for people to wrap their heads around, because we tend to think that if I see a sentence, I know the meaning. I know what each word means. You don't know how you acquire that meaning. You actually acquire that meaning by using those words being used in various contexts, and then you learn the meaning of it that way. You don't remember that. So people tend to think that essentially each word has like some simple meaning, but the meaning actually evolved by the use of the term. How many of you know the very first dictionary of English? Oxford English Dictionary. Actually, it's like before that was Johnson's dictionary. But Oxford English Dictionary is considered like the first big dictionary. And the way they actually wrote the dictionary, it's like there's a beautiful book called The Professor and the Madman. If you get a chance, read it. And what OET did was it said, we will try to understand meaning not by fiat, not by saying this shall mean this, but by looking at what people are using the words in the context of. Now, this is something that you guys say, that's a big deal, we just crawl the web and we'll know how people are using. This is Oxford English Dictionary we are talking about. There was no computer. People were doing their own usages in their own local circles. So to understand usage of words, people had to go see various printed papers, newspapers or something, and see how was it used. And so instead of a program crawling the web, people would be paid, people would volunteer to say, okay, here are all the 15 different uses of this word that I have seen in the number of recent newspapers that I have had the chance to read. Okay? And in fact, the story of the professor and the madman is there's this one guy who is in a lunatic asylum who had a lot of time on his hands. And he actually was like the biggest crawler for the OED. He wound up providing the usage cases for many, many, many words that took part in the first Oxford English Dictionary. Now, all of this sounds anticlimactic to you guys because you are in the generation of web. How many of you have heard of this idea called word vectors? Okay, so the word vectors essentially basically say that you can figure out what a word means by essentially getting the entire corpus of English that is available on the web. So there is a Wikipedia corpus. So get all the Wikipedia articles. That has about 9 billion tokens or something. Or you can get all the Wikipedia, newspapers and everything else on the web that you can crawl. That's about 42 billion tokens. Token means, words. Okay? So you take these sentences and then you realize how these words are being used in the context of other words. And without giving any information about what meaning is in English, word vectors essentially just figure out, because they have access to this 42 billion token corpus, they sort of manage to figure out that, for example, king is, for example, what? Man is to woman as king is to, and you'll be able to say king is to king. Without knowing anything, nobody put any input knowledge at all other than just looking at the raw sentences on the web. Okay? So we take this for granted right now. But really this corresponds to the small question that somebody asked. Do we write the meanings of anything? No. Meanings evolve. Dictionaries are trailing indicators of the usage of language, not the leading indicators. There have been words that were supposed to have a good connotation, but people started using it in the bad way. And so dictionaries say, yeah, now that word is actually not a compliment. Don't say it to your boyfriend. Okay? So dictionaries are the trailing indicators. You no longer need dictionaries in the context of these kinds of web dictionaries. Yes, sir. Yeah.
Okay. Is this getting into like the concept of the semantic web with like RDF triples?
We will also talk about semantic web. Okay. We'll talk about everything in today's class. You may or may not go home, but we'll talk about everything. Yes. It's connected to semantic web, it's also connected to distributional semantics, but in very different ways. Any other question?
The word vectors, is that the sort of the leading technique of NLP?